Hey guys, welcome back to another video of Calculus 1 / AP Calculus AB. In today's video, I'm going to be talking about continuity. But before we begin, we should do a recap of one-sided limits. So these are limits that approach a value from only one side of C instead of both. And they are written as the limit of f of x as x approaches C from the left, or the limit of f of x as x approaches C from the right. And what I just said is over here. A limit exists if these conditions are met. So it says if f is a function and c and l are real numbers, then the limit of f of x as x approaches c is L if the limit of f of x as x approaches c from the left is equal to L and is equal to the limit of f of x as x approaches c from the right. So that means that limits from both the left and right sides of c must be equal to each other in order for the limit to exist. So as you can see here in this graph, we have the function y equals x minus 1. And over here we can see that we're trying to find the limit as we get closer and closer to 1. So right here it says the limit of x minus 1 as we approach 1 from the left gets closer and closer to 0, so it reaches 0. And it says that it's equal to the limit of x minus 1 as we approach x from the right. As you can see, they both approach the same value, which means that the limit does exist. So if the left limits and the right limits are the same, they reach the same value, then that means that the limit does exist. Okay, so now let's talk about infinite limits. An infinite limit occurs when the value of a function increases or decreases without bound. So either goes to positive infinity or negative infinity as x gets closer and closer to c. So in other words, instead of the function approaching a single finite number, it grows larger and larger without bound. So over here we have the function 1 over x, and we're trying to see what happens when you get closer and closer to x equals 0. So from the left, the limit of 1 over x as x approaches 0 from the left, it gets closer and closer to negative infinity. Because if you were to plug in some value for x like negative 0.00001, you're going to get like some big number that's like 100,000. So as you add more and more zeros, as you get like closer and closer to 0, that number is going to approach negative infinity. Sorry, I meant to put a negative sign over here because there's a negative over here. And the limit of 1 over x as you approach 0 from the right is equal to positive infinity, because you're basically dividing 1 over 0.0000001. And that's like 100,000 or like a million, and just keeps on going on. But since they approach two different values, the limit does not exist. The limit of 1 over x as x approaches 0 does not exist. So let's talk more about infinity. So limits that approach infinity technically do not exist because the limit has to approach a single finite number. Because of this, the symbols negative infinity and positive infinity are used to describe the unbounded behavior of the function and hope to explain why the limit does not exist. Okay, so these are some properties of infinity, and if we let the limit of f of x as x gets closer and closer to c equal to L, and if we let the limit of g of x as x approaches c equal to infinity, then the limit of f of x over g of x as x approaches c is equal to 0. Down here, in polynomials, the highest degree term dominates the function's behavior. So assuming that the highest degree term of f of x is positive, then the limit of f of x as x approaches infinity is also equal to infinity. So let's say f of x is like equal to x cubed, right? As you get closer and closer to infinity, this would be some huge number cubed. So as you get like bigger and bigger, you're going to approach infinity. And the same thing can be said if you go to negative infinity. So you have x cubed. If you approach negative infinity for x, you also go to negative infinity for y. And the signs can be switched based on the sign of the highest degree terms. Like imagine f of x is equal to, let's say, negative x to the power of 4, right? And as we approach infinity, we get some huge number, but towards the negative infinity. Okay, so now let's talk about the definition of vertical asymptotes. If f of x approaches positive infinity or negative infinity as x approaches c from the left or right, then x equals c is a vertical asymptote of the graph of f of x. Another way to define vertical asymptotes is by using graphs or like functions. So let's say we have a function h of x, which is equal to f of x divided by g of x, and if f of x is not equal to 0, but g of x is equal to 0, and the limit of h of x approaches positive infinity or negative infinity as x gets closer and closer to c, then the graph of h of x has vertical asymptote at x equals c. So to see that visually, let's say we have like the graph of 1 over x squared. It would be something like this. So as we get closer and closer to c, let's say c is equal to 0. So x approaches 0. So as you can see, the graph, as you get closer to c, this is c right here, 0 in the middle. You get close to infinity. And the same thing happens over here too, which means that there's a vertical asymptote over here because there's like some line that the function will never reach because 1 over 0 is undefined. Okay, so now let's finally talk about the definition of continuity. A function f is continuous at x equals c if all three of these conditions are met. F of c is defined, the limit of f of x as x approaches c exists, and the limit of f of x as x approaches c is equal to f of c. And to see that like simply, in a simpler form, this just says the conditions for continuity. The first one is f of c exists, the second one is the limit of f of x as x approaches c exists, and the third one is the limit of f of x as x approaches c is equal to f of c. So now let's talk about discontinuities. A function at x equals c can be discontinuous for any of three reasons. F of c is not defined at x equals c, the limit of f of x does not exist at x equals c, or f of c is not equal to the limit of f of x as x approaches c. So for the first reason, f of c is not defined at x equals c. So let's say c is equal to 0, which is right here. So we can see that there's a hole, but the limit does exist because we approach 0. But f of c does not exist, which means that it's continuous, or that there's like a hole in the graph. So an example reason 2 is that the limit does not exist at x equals c. So in order for the limit to exist, the left and right sides of the limit must be equal. But as you can see here, the left side of the limit approaches 0, but the right side of the limit approaches 1. And 1 is not the same thing as 0, which means that the limit doesn't exist. And for the third reason, f of c is not equal to the limit of f of x as x approaches c. So right here, we see that the function gets closer and closer and closer to 0. However, f of c is defined at -3. And since the limit has to equal f of c, the function is discontinuous at x equals 0 because the limit is not the same thing as the function. Okay, so there are two kinds of discontinuities. The first one is a removable discontinuity, where f of x can be made continuous at x equals c by rewriting it. So in other words, we can rewrite f of x so that f of c is equal to the limit at x equals c. The second kind of discontinuity is a non-removable discontinuity. Is when a function cannot be rewritten to make x equals c continuous. It is also when a function approaches infinity or has a jump in its graph. So we have this function to our right that is equal to x plus 1 over x squared plus 3x plus 2. So we're trying to find out the continuity of this graph. So let's see if there's any removable discontinuities where we can rewrite the graph so that it's still continuous. So in order to rewrite it, we can factor it. So as you can see here, we can factor this out into x plus 1 times x plus 2. So we have 2, and 1 factors of 2 add up to 3, 2 and 1. So we have this over here. But since we have x plus 1 on the top and x plus 1 on the bottom, they can be canceled out. And now we have 1 over x plus 2, but x cannot be equal to -1 because although we simplified it, this just tells us that f of x is not continuous -1, that it can't be this, so that we can preserve our original function. Okay, so now we have determined that x equals -1 is a removable discontinuity because if we redefined f of -1 using the new function, it would be continuous. So let's plug in f of -1. So we have 1 over x plus 2, that's equal to 1 over -1 plus 2, and that's the same thing as 1 over 1 or 1. So as you can see here, -1 is over here, and the function seems to be equal to 1, but there's a hole right here because it's undefined at -1, because the denominator is equal to 0 at -1. So there's a hole right there, or a removable discontinuity. Okay, so now let's see what happens over here. So you can see there's like a gap in the function, which means that there's likely an infinity discontinuity, and all infinity discontinuities are non-removable. So as you can see here, at x equals -2, the denominator becomes 0, while the numerator does not equal 0. This means that the function goes to infinity, and that this is a non-removable infinite discontinuity. So if we plug in -2 for f of x, we get 1 over x plus 2, that's equal to 1 over -2 plus 2, and that's equal to 1 over 0, which does not exist. So in summary, f of x is continuous everywhere except that x equals -1 over here, and that x equals -2, this whole asymptote right here. So there's a removable discontinuity at x equals -1, and a non-removable infinite discontinuity at x equals -2. So that's it for this question. Okay, so now let's talk about continuity on an interval. A function is continuous on an open interval a, b if it is continuous at every single point inside the interval. So imagine we have like some function, and this is a, and this is b, and if it's continuous for everything inside of it, then if every single point is continuous inside of it, then that means that whole interval is continuous. And up here it says that a function is continuous on a closed interval ab if it is continuous on the open interval ab, and that the limit of f of x as x approaches a from the right is equal to f of a, and that the limit of f of x as we approach b from the left is equal to f of b. So imagine we have like this interval, we have a and b. So do we have like some function? It like touches here, it's continuous, and it touches here as well. So like this is b, and this is the limit from the left of b. So you approach b from the left, and the limit of as you approach a from the right is when you go to here. Okay, so now let's talk about some properties of continuity. If f of x and g of x are continuous at x equals c, then f of x plus g of x is continuous at c, f of x minus g of x is continuous at c, f of x times g of x is continuous at c, f of x divided by g of x is continuous at c if g of c does not equal 0. And lastly, if g is continuous at c and f of x is continuous at g of c, then f of g of x is continuous at c. So let's show an example of the first property. So let's say h of x is equal to f of x plus g of x. Let's say f of x is equal to x, which is this red line down here, which is continuous at 1. So we're going to be looking at 1, x equals 1. And g of x is equal to 1, so it's just a straight constant line. So we're both looking at 1, and they're both continuous at x equals 1. So h of x, which is just a combination of both of them, is also continuous at x equals 1, which is just this black line over here. So you can see it's continuous because the limit exists and it's defined right there. Okay, so now let's talk about the greatest integer function. This is often denoted as double absolute value of x, or like this. And it's a function that inputs a real number x and outputs the largest integer that is less than or equal to x. So in other words, it rounds a number down to the nearest integer. So imagine we have like 1. So 1 is right here, but the greatest integer that's less than 1 is just 1 itself. But let's say we have 0.5. So the greatest integer that's less than or equal to 0.5 is 0. It can't be 1 because that's greater than. So yeah. So let's do some other examples of it. So let's say f of x is equal to the greatest integer function. So let's find f of 3.7. 3.7 is over here. As you can see here, the greatest integer less than or equal to 3.7 is 3, which gives us our answer over here. So now let's find f of negative 1.2. So we're at negative 1, negative 1.2. But since it's negative 1.2, and the greatest integer that's less than or equal to negative 1.2 is going to be negative 2, because it's over here, but you can't go higher up, which means you have to go down. So you have negative 2, And now let's find f of 5. So we have 1, 2, 3, 4, 5. F of 5 up here is just going to be itself, f of 5. So now let's find some limits for the greatest integer function. So let's find the limit of the greatest integer function as x approaches 2.3. So we have 2.3 is over here, and as we approach 2.3, that's just going to be equal to 2 right here, because you can see that in the graph. So some like simple formulas that you can use when evaluating the greatest integer function is that the limit of the greatest integer function as you approach some value n from the left is just n minus 1, and the limit of the greatest integer function as you approach n from the right is just equal to n itself. So now I'll try it for 3 from the left. So we're approaching 3 from the left side, and 3 is right here, but we're approaching it from the left. So we get closer and closer and closer to here. But as you can see, this is 2. Or you can say that it's 3 minus 1, which is also 2. Okay, so now let's talk about this last limit. So we're looking at the limit of the greatest integer function as we approach 3 from the right. So 3 is over here, and we're approaching it from the right. As you can see here, we reach 3, or just n. So yeah. So now let's do some more complex limits. So let's find the limit of 6 times the greatest integer function minus 7 as you approach negative 2 from the right side. So if you recall here, if you approach something from the right side, it's just going to be itself. So you have 6 times negative 2 times negative 7. So you get negative 12 minus 7, which is just negative 19. So now let's do this bottom one over here. So we're looking for the same thing, but we approach negative 2 from the left. If you recall, if you approach something from the left, you just subtract n minus, you just subtract 1 from n. So let's plug in 6 times negative 2 minus 1 minus 7. So we get 6 times negative 3 minus 7. We get negative 18 minus 7, which is equal to negative 25, which is our answer. Okay, so now let's talk about the last part of today's lesson, which is the intermediate value theorem, which basically states if a function f of x is continuous on a closed interval ab, and f of a is not equal to f of b, and k is any number between f of a and f of b, then there exists at least one number c in the interval ab such that f of c equals k. So in other words, a continuous function reaches every value between f of a and f of b at least once. So as you can see here, let's say we have a is over here is like equal to 1, and b is over here is equal to like 3, right? So if it's continuous, at some point you have to cross like 2, because 3 is up here and 1 is down here. So at some point, some c, you're going to cross 2, which is basically your k here. Additionally, if f is continuous on AB and f of a and f of b differ in sign, then the intermediate value theorem guarantees the existence of at least one zero of f of x in the closed interval AB. So let's say we have a is up here and b is down here, but since it's continuous, it has to cross the x-axis at least once, because if it wasn't continuous, it would just skip through it. So let's do this example. So we need to find the value of c in the interval 0 to 6 where f of c is equal to 0. So for our first step, we need to make sure that f of x is continuous on AB. But since this is a polynomial, and polynomials are continuous for all of its domain, because it will never be not continuous, because it's just, you know, it just goes on for a while, it just goes on forever. It has no holes in its graph. And for our second step, we need to make sure that f of a does not equal f of b. So let's plug in f of a. Our a is going to be equal to 0, and our b is going to be equal to 6. So f of 0 is 0 plus 0 minus 12, which is a negative 12. And f of b, which is just 6, is f of 6, which is 36 plus 6 minus 12, or 42 minus 12, which is 30. And for our third step, if both tests pass, like step 1 and step 2 pass, like they don't equal each other and it's continuous, then you can stop for c. So let's put in f of c, which is equal to 0. We get c squared plus c minus 12. We factor out, we get c plus 4, c minus 3. And we get that c is equal to negative 4. and 3, but since only 3 is inside of 0 to 6, c is equal to 3. So now let's look at some cases where the intermediate value theorem does not work. The intermediate value theorem fails when f of a equals f of b, or when f of x is not continuous on ab. So let's see the function f of x, which is x plus 2 squared times x minus 2 squared divided by x plus 1 squared on the interval -2 to 2. So this interval over here. So we need to find c when f of c is equal to -6. So it's somewhere over here we're trying to see if it equals -6. But this doesn't work because f of x is discontinuous at x equals -1. Because if you put -1 into here, you basically divide by 0, but that's undefined. And if it's undefined, that means there's a hole in the graph, which means that it's not continuous, and so that the theorem fails. Also, f of -2 is equal to f of 2. So you can see right here, these two are basically the same thing. So the theorem fails for 2 reasons in this graph. Okay guys, thank you for watching this video. This is just the first part where I just teach a lesson. The second part will cover some of the questions related to this section. But thank you for watching, and stay tuned for more videos.